This is our second session for our Innovation Forum, and we would like to start off some high-level topics. Last week's, if you weren't able to attend, I believe it's recorded, you can review it any time. But we kind of jumped right into a particular notebook, a particular set of analysis on RFM analysis. So please feel free to review that if you haven't had a chance to look at that. But we are going to talk a little bit about just some high-level concepts at the beginning of this. Talk about what is machine learning, whether or not you're using it today. We do want this to be interactive. We do want there to be some back and forth, and hopefully as we progress these over time, things will become more interactive and more community-based. But for these first few, certainly we're happy to seed some of these conversations and come up with some of these topics and share some of our knowledge with it. So talking about machine learning, if it's new to you, there are two basic broad categories of machine learning. One is unsupervised. This is a lot of novices to machine learning or AI think this is kind of how this works, is that we can simply take tools and point them to data and they will tell us something that we did not know. And that is what we call unsupervised learning. It doesn't take a lot of human labeling of data. We don't have to categorize our data. We can simply point to the data and we can potentially run clustering. So that is where we can, based on a number of different data points, find all of the patterns of all of the different data points together and distill that down into a single cluster, right? So we didn't have to decide what that cluster is, you know, whether it's giant firms who are international, who use litigation and real estate. That potentially could be a cluster. I don't know, right? Conceptually, that's something that could come out. We didn't have to come up with that category of clients. That's just as we point these algorithms to our data and run it, it will derive that cluster of data if such a thing exists. So that's the idea of unsupervised machine learning, where we don't need to label those categories. We don't need to come up with a particular category before we run the analysis. The clustering algorithm will actually come up with the clusters for us. We can massage things and come up with a number of clusters we suggest, but we kind of work through those things as a data scientist to come up with some optimal results. Another one is dimensional reduction. So this is something that is some of my favorite things to do with machine learning and some of the AI tools. This is our ability to point these algorithms to our data, and based on a number of disparate features, it will come up with a single dimension. It will derive everything down. So imagine if you can, in a more classic business intelligence or business analyst role, where you're combining location, client rank, and top practice, right? Let's pretend you took those three dimensions of practice, the rank, and where they fell within the firm for location, and you combine those into a single dimension of location, practice, rank. We're kind of doing that, but on all the data at once. So things like billings, things like realization, utilization, profitability, all the disparate pieces of activity can be used to derive that single dimension. So as we work through our dimensional reduction, it will decide how much variability is removed from the model. And I'll talk a little bit about that more, but dimensional reduction is something we can do with unsupervised learning. Association is another one. This is your classic market basket analysis. Just as Amazon will tell you, people that purchase these books will often purchase these books together. It's not just books anymore, but that type of market basket analysis is something we can do with unsupervised learning. Another major category is supervised learning. This is where we have gone through and we have some type of labeling of our data potentially, where you have come up with categories. So I've decided that that's a premium client. And potentially I've decided what defines a premium client. Could be the amount of revenue, could be the amount of profitability, could be the number of unique matters or practices. But based on some criteria of a formula, I've derived that's a premium client. Based on all of my premium clients in the past and based on all those attributes, we can feed that information into the machine learning models. It can kick back, and as a new client comes in, based on all of the potential features that we set into the model, it will decide what its category will be. It's predicting its category based on your past prediction, your past labels, I should say, within the model. So that's something where we call that classification. So that is a supervised machine learning model. And another one would be regression. This is typically used for a lot of linear regression, temporal analysis. We're doing something over time. Potentially we want to predict things in the future. So based on how things have behaved in the past, we will predict what's going to happen in the future. And so that is generally done with regression, which is another set of models and algorithms available to us. But I would also say, you know, that is also potentially a novice coming into AI and machine learning, potentially with their view of what AI should be, right? That it should be predicting things for us, right? It should be learning from the data and be able to come up with predictions based on what it finds. So I just want to group those two major groups of machine learning together, but also hopefully in terms that everyone can understand, right? That the idea that it's going to find some really interesting pattern in the data that I was not aware of, that is unsupervised learning. It's going to run predictions and tell me the future based on everything I feed into it. That is supervised learning. Okay, moving along. So now we have our first poll. Again, we would like this to be interactive. So if you can, feel free to read it, answer it yourself. But we would like to know, are you using any machine learning? Are you using AI? Or are you using both? Or potentially no, not yet. We're not looking at those yet. And so I will pause for a second and allow people to answer the question. And we would like to capture some of these results if we can in general.
Hey, Greg, just a quick question. Would you mind spending just a minute to break down the difference between AI and ML?
Yeah, that's a great question. So within the categories of machine learning and AI, we often use the terms a bit interchangeably. In broad strokes, there's really three categories. The largest, well, if you're imagining a Venn diagram of AI and machine learning is a circle inside the AI circle. Some people call AI just whatever we're doing is next. You know, it's the future. It's always the bleeding edge. They just anything in the future is AI. That's one terminology for it. Another more classic one is that, you know, it is trying to recreate human behavior as it comes to predicting decisions, right? We're going to feed some information into the system. It's going to give us some type of a decision out of it. So it's trying to recreate that human behavior of making decisions or suggestions based on information. So the simplest of that could simply be a rules engine. So potentially even a workflow engine, where we have a number of questions, if-then statements, and based on what we feed in, it's going to come back with the correct response. If this is a litigation matter, if it has not gone through a conflicts check, you should go through a conflicts check. That type of computed decisions all of it falls under AI. Machine learning is a circle within that, where instead of coding out those rules, where we know the business rules we want to capture, we know the predicted behavior we want to happen in the system, we're going to codify those rules. With machine learning, we have algorithms that we point to the data, and it's going to derive the suggested behavior, the suggested decision. It's going to come out with the category. It's going to derive the cluster. It's going to derive the principal component, where it's going to do those things based on the data, based on statistical analysis. And finally, beneath machine learning, there's another kind of unique set called deep learning. Deep learning is typically where we're really trying to not just replace decision-based behavior from humans, we're really trying to replace human capabilities for things like image recognition, language understanding, so being able to actually look at an image and recognize someone's face, being able to listen to audio and transcribe that back into English. Those are typically using deep learning techniques, which are often using neural network analysis, which is basically trying to recreate how the human brain works. We call that deep learning. So it's quite advanced in what it's doing from a technical stack, as well as the algorithms, but also, it's also very specific use cases, typically images, language, some very specific things that humans do. Okay.
Really quickly, I'm sharing the results.
These the results? So for the results, yes, we're using ML and AI, 8%. No, not yet, 92%. Well, I'm very happy to not hear that. I am happy that I'm starting at such a high level today to talk about some of these higher concepts. I think last time I jumped into an actual working notebook. I just want to make sure that everyone's getting what they can out of these sessions and that it is as interactive as possible. So I would like to make sure everybody feels we're addressing any of their questions today. Another question, if you can, answer this in the chat. So we're not going to pause for the poll, but we would like to capture this in the chat. Are there any applications you're aware of using AI at your firm? So this is a bit of a departure where instead of what we've been talking about is using, as a data scientist, using machine learning, using AI internally in your own internal based analysis. What we often see is that a lot of firms are purchasing software from vendors that then has AI baked into it, right? So IntroHive is one that jumps out. They're a firm we've worked with in the past where they scrape all of your exchange data for relationships. And I got to tell you, the real value is in that exchange data, right? The value is in that data. The fact that they unlock it is the value they bring. But then they do some things that are specific that certainly you could consider very valuable to you. One of them is it computes your relationship score. So it's got some sort of, business intelligence type applications where it's got a formula it's running and what is the relationship with this person. It's trying to compute those answers for you. That's kind of what I would call BI, where we're really, we know the business problems we're trying to solve. We know the business questions and we're deriving solutions for it. But then they also do things like AI, where they will suggest contexts. So that is something where they're running AI on top of your data, and their engine is suggesting the fact that you should create an exchange contact and sync it into your CRM. So that's something where it's, it's not just a formula, it's not just some computed number, X times Y equals 12. It is actually running AI and it's making suggestions to how the workflow should work on top of your contacts and where they belong in your CRM. What do data scientists do? So again, breaking this down a little bit, I find data scientists is kind of an unknown to a lot of people. What is it that they do? And so I would say that a typical data scientist, and again, there's maturity with how long they've been working and projects they've been on and all those things. But conceptually, they have to wear many different hats. A data scientist has to do all the jobs a data engineer would do. So someone that's building a data warehouse, someone that's building a big integration for you, someone that's potentially building a reporting table, converting a system. Those are all data engineers. We're moving data from A to B in a very programmatic way and have very technical skills. Experts on data, experts on schemas, et cetera. A data scientist is someone that needs to be able to do all those things, but for their own purpose. And so one of the big differences that you'll hear me talk about in these tools and technologies is schema on read versus schema on write. Schema on write is our classic business intelligence. It's potentially a data warehouse. It is a queue. We have defined the output that we want our data to go into, and we are going to map and transform our data into that output. That is data engineering, that is data warehousing, that is business intelligence, and we call that schema on write, where we've defined the output before we build our ETL. Schema on read is really something that comes with data scientists and data lake technology, where we land our data somewhere. For your data scientists who are kind of, on their own, potentially at a firm, this just might be Excel files, right? It could just be a bunch of Excel, could be a bunch of CSVs, could just be extracts. Someone's manually shipping them, emailing them around for, an ad hoc set of questions. So they have to determine the schema. They have to decide what's in the data. They have to determine where the data came from, what the data formats are in that data. Right, Excel or a CSV is not going to communicate that information with it. It's not going to tell us that that is a numeric piece of data versus text. If anyone had a lead enterprise, I'm sure you've truncated the timekeeper initials a million times. That type of schema information does not come along with our Excel and CSV data. So our data scientists have to read all that data and mash it up on their own. So that is something data scientists will typically do in general, is they're working with kind of unknown data to a degree. Data cleansing and transformation. So this is something where, again, our data engineers do this work as well, but our data scientists are going to have to do these things specific to what they're going to do statistically. I'll talk a little bit more about that. The statistical analysis, this is the idea that a business analyst with a BI solution knows the business system. They have business acumen on the system. Let's say it's your financial system, clients, matters, timekeepers, time cards, cost cards. They understand these concepts, bills that go out, collections that come in. They understand these concepts. They understand the meaning of them, when they happen. They understand some derived calculations and the value of them. For example, utilization, realization, days to collect, some derived statistics. They could ask for those things from the data engineer. The business analyst is going to ask for them. The data engineer is going to design it. They're going to populate a schema with it. And then the business analyst can, without any other technical help, ask these questions and answer them. And that's what typically a Q will give you, but it could just be a pivot table in Excel. For this example, they can ask the question, decide who my top 10 clients are by billings, decide who's our latest to pay based on days to collect. They can answer these business questions on their own with a BI solution. A data scientist will often have no idea what they're getting. They could be getting financial statistics. They could be getting CRM data. They could be getting a set of contracts from out of the DMS. And they're going to apply the same statistical analysis to all of it. So they can explore the data statistically. They're not just going to look for the average bill rate or the count of matters by client that a business analyst might ask. They're going to look at the count of all of the fields, the count of clients, the count of matters, the count of timekeepers, the count of industries. They're going to look at everything statistically to get a view of what's inside my data. So data scientists are often exposed to many disparate data sources and not just something they have a lot of business acumen on. Machine learning engineering, this is where we've decided to build a machine learning model. For example, client categorization, like we discussed earlier, and actually operationalize that. Instead of the data scientists doing that every time a new client comes in, we'll actually take that machine learning model, deploy it in the cloud, potentially have an endpoint, and as your new business intake comes in, we can ship that out and say, here are the attributes that matter, and the ML model will come back and say, well, this is the client category. So machine learning engineering is sort of the operational discipline of taking all that ad hoc work a data scientist has done and operationalizing it into some type of an endpoint that could be called in your day-to-day workflows. So that is machine learning engineering. And often it's the same person, right? The data scientist will build something of value, and then they might spend a month operationalizing it. The other piece is science itself. This is really where the title comes from. When we're running predictions, when we're doing things within that supervised learning track, we are going to run experiments. So we're actually going to run experiments, come up with a hypothesis, run experiments, find the results, find out if they validate, and keep iterating. So we're really following the scientific method in our machine learning development. So we're actually going to build experiments and run them. A part of that is repeating the results. In normal sciences, you're going to describe all the data that you have, describe the materials, describe the portions of them, and be able to run an experiment. In data science, we have to track the versions of the models. We potentially have to track versions of the data. So the fact that our data can change over time, potentially daily, these become problematic when it comes to data science and our ability to run these experiments. So just be aware, a huge part of what data scientists do and spend their time on is simply being able to recreate those experiments in a scientific way. So question, does anybody use data scientists today? Expect this to track similar. So 25 and 75. All right, so this is higher, so this is good. This is good. So the next big question I have for you then would be if we now have, instead of using ML at 8%, data scientists at 25, what department is hiring your data scientists? So is this something coming out of the finance function? Is it coming out of knowledge management? Is it out of your application development team? We certainly know of firms who have data scientists that work in some type of litigation support. You know, they work for the attorneys. So that could be a department that's hiring our data scientists first. So that's a question we have is, you know, what department potentially is hiring your data scientists, if you know. So talk a little bit more about some of the individual pieces, and we can have whole sessions on these. You know, the data cleaning, just some pieces that to be aware of what a data scientist is going to do different than your data engineer. Is that we're going to remove outliers. We're going to transform and shape the data for the machine learning models. Conceptually, just imagine all the text that we do, all the unstructured data that we do. We actually eventually infer structure. We programmatically build structure around it, and then we programmatically turn text into numbers. So we are going to go through and transform data, not just in a way a business intelligence developer would for the business questions. We're going to do things purely so that you can run these statistical formulas on them. And so there's a lot of things that data scientists do around shaping of data and transforming data that has nothing to do with anything other than getting it into the right format for machine learning. We also have the exploratory data analysis. I mentioned the statistical correlation I want to focus on because we are going to talk about that, and the dimensional reduction of PCA. So PCA is principal component analysis. And here's an example of what happens when we run PCA on top of something. Within the data, it comes up with a single new principal component that will eliminate a particular amount of variance. In my best models, you know, or you know, my best PCAs, I should say, it'd be something maybe I'm looking at 30% of the models are reduced by one principal component, 50% of the models by two. So just be aware that PCA analysis allows us to come up with these new dimensions to group and categorize our data. That is done in an unsupervised way, where then we can leverage that in further analysis like clustering. So I could first derive these new dimensions, then cluster on top of them. Some tools, what are we using? R, Python, and Spark are the big tools I use all the time. R is a statistical language where we do statistical analysis. Python is an open language that can be used for anything, even web development, but it has a bunch of statistical packages that have been built. So it's a very simple language, so it's a very popular one with data science now. It's easy to learn, and they have very advanced packages that sit on top of it. As I mentioned, notebooks are something that's a little bit different, where we, or maybe I did mention some, notebooks are something a little bit different where our developers are actually able to put code and the results together in a single file. And so we use notebooks to show our code, show the progressions, show the transformations, show the model as it's built, and show the results all in one file. And so those are called notebooks. And this is an example of a Jupyter notebook where I have a line of code that is then giving me a chart output. And this is the kind of side-by-side analysis a data scientist will do that's closer to, I would say, like a business analyst in Excel, right? Where they can do the formulas, the presentation, and the annotation together in a single file. And we can do all of that in notebooks. Talking about what we actually did for this week. So we have a marketing ROI where we've combined campaign data with ERM data with financial data. So whether you use Vuture or HubSpot, Click Dimensions, IntroHive, Grabit for your relationships, we're able to combine all that data together in one particular piece of analysis. So next question, do you currently capture ERM? So again, IntroHive is probably the most popular one I know of. Intap Relationships is coming with Intap. Grabit was out there and pretty popular. Client Sense and Nexel, you certainly see in the market. So there's definitely firms doing it in general. I got to say, yeah, I'm really excited about this data. I find that all of my analysis, my ERM data enriches it all. So 50%, that is fantastic to hear. If you're not looking at ERMs, I would suggest it. It's really just, it enriches all of your client level analysis, all of your business development analysis. And I don't want to say it's for free because it costs money, but it scrapes the system. We don't have to get the attorneys to try and input stuff. I think that's the biggest advantage. So another question, are you using opportunities? Most of my clients are no. They're not tracking opportunities, or certainly not firm-wide. There might be some minimal opportunity adoption within the firm, but you got to admit this is higher than what I was expecting at 42% right now. More of our clients are using opportunities than I expected. And so that's something that I find is really interesting because, obviously if you're tracking opportunities correctly, you can really find out the return on your investment of some of your marketing campaigns. But for the firms that aren't, we're able to statistically pull some of this stuff together. So what kind of tools you use for managing campaign, Future, HubSpot? Feel free to answer in the chat. So the output of this results is our correlation heat map, where we actually have, if you're not familiar with the heat map, if you're not familiar with a parallelogram, this is really a mirror image of itself. So everything to the top and to the right is mirrored by the left and to the bottom. So you can just focus on one particular column or one particular row. So looking at bill amount, it's really interesting to see what comes out that correlates with it. Activities from my CRM, the estimates, not my budget's tied to my amounts, not too surprising. My relationships from my ERM, so the relationships I scraped, the contacts for my CRM versus potentially BD specific activities from my CRM. So it's really interesting to see which of your investments, whether it's through the campaigns, whether it's through the marketing BD efforts, whether it's the events itself, versus the partner relationships, which we can break out, which of those have the strongest correlation to our billings. And then based on this, we were able to then do some client segmentation and clustering. And in this particular analysis, I'm looking at my bill amount versus my CRM activities, but you can see these things flow together in a nice correlation plot here, a scatter plot here, where you can see how these things flow together, and we derive that from that correlation first to then build this into our client segmentation and clustering. So again, this is something where you can just see we can apply these machine learning models and techniques as a data scientist to our data and come up with some new interesting insights that we were really never able to do as a business analyst. Okay, I'll stop there. Does anyone have any further questions or anything in the chat, Liz?
Yeah, we had a question come in that I was just typing an answer to, where they're looking to find more information about the marketing ROI slide that you presented. So just some interest in that.
Sure. Yeah. No. Happy to have an offline session about the diagram itself.
And I was excitedly typing, let's do a session just on that.
Yeah. And that sounds good. Yeah.